Broadcast is now starting. All attendees are in listen-only mode.
There we go. Well, okay. Welcome everybody. A couple minutes late getting started here, but I think we're all ready to go. So, welcome to the week 3 for S2S webinar series. Now, I think most people here, many people here at least, have probably attended before, so you know that this is a monthly series, and it's co-sponsored by OAR Weather Program Office S2S program and the NWS OSTI modeling program. I'm Mark Olson from the WPO S2S program. And before we begin, I wanted to remind everyone of the webinar series website, and I'll post the address in the chat box here shortly after I get done speaking. And on the site, you can find the information on the upcoming talks. You can join the mailing list for these notifications of the webinars. You can get recordings with past talks, and there's also a forum if you're interested in presenting at a future webinar too. So I urge you to take advantage of that. Finally, if you have questions for the speakers during the presentation, post them in the discussion document. That's actually should be linked in the chat box there, and I'll probably periodically throw it in the chat box, just kind of keep reminding you. And probably actually need to get it set up. I did not get a chance to get it set up with the spots for questions for these speakers, so we'll do that here shortly as well. So anyway, today we have two presentations. First of all, we'll start with Prashant, and you're going to have to excuse me. Sardeshmukh. Is that
Sardeshmukh.
okay? Sorry about that. But he will speak about accounting for chaotic physics in atmospheric models, and after that, Rochelle Worsnop will speak about their work on neural network-based processing methods. So we'll go ahead and get started. I'm going to turn it over to Prashant, and let me make him presenter here so he can share his screen. And there, you should be able to go ahead and present.
Okay, do you want me to start?
Yep, go ahead. Yep.
So, thank you and good afternoon, everyone.
We can't see your screen quite yet.
Okay.
So you have to do the show your screen button again as we did before.
Oh, something happened here again.
I think I had switched it off when we were testing Rochelle.
So again, how did I do that? Okay, let's, yeah, show my screen. Is that good?
Yep, perfect. There you go.
Great.
Yep. Okay, great. Thanks.
Okay. Good afternoon, everyone. This is joint work with my long-term colleagues, Erin Wong, Gil Compo, and Cecile Penland. And this is the outline of the talk. So we all know that weather and climate predictions are inherently probabilistic. And in practice, the forecast probability distributions are estimated using a finite ensemble of forecasts from slightly different initial conditions. And such ensemble forecasts are known to be overconfident in general, in the sense that reality too often falls outside the forecast uncertainty indicated by the ensemble spread. And when averaged over many cases, the RMS error, root mean square error of the ensemble mean forecast is always found to be larger than the ensemble spread. And one popular way to reduce this gap between the forecast error and the spread is to stochastically perturb the forecast model's parameterized diabatic tendencies. And many studies have shown that this robustly increases the forecast spread, and less clearly, it sometimes also reduces the forecast error. However, I want to show that we find clear reductions of forecast errors in large ensembles of 15-day GFS forecasts. And I want to argue that they arise in effect from improving the model's deterministic evolution operator by stochastic noise-induced drifts. And we also find significant impacts of such stochastic perturbations on the mean climate and variability of the FV3 GFS model. Sorry, how do I advance this now? I can't seem to advance this. Right. So this is just by way of framing the issue visually. In the real world, if you were to start off with a delta function initial condition shown by the the blue vertical bar at the left, then because of the chaos in the atmosphere, the conditional probability distribution at some future time shown by the blue curve here has a finite width, and at some later time it asymptotes to the climatological probability distribution shown on the right when all predictability is lost, both deterministic as well as probabilistic. And of course, we don't have a perfect model or perfect initial conditions. So if you start off with some finite initial kind of spread shown by this dashed curve in the left, then our forecast, the ensemble forecast, evolve into this dashed probability distribution, which does not match the true distribution, but we don't know what that true distribution is. We only know the error of the forecast, either say the ensemble mean forecast as the best forecast, and we also know the ensemble spread. And so how do we know that we are making a mistake, and how big is that mistake? And so you can't say in an individual case, but if you look at these results over many forecast cases and look at the growth of the forecast ensemble mean forecast error over those cases, and also then compare it with the spread, ensemble spread averaged over many cases, then you get these two sorts of curves you see at the bottom of the picture. And if the spread is generally too small, too weak, then the telltale sign of that is that it will always lie below this red curve, the error curve. And so the gap between these curves indicates the potential for forecast improvement. So an increasingly popular approach to reducing this gap is to introduce additional stochastic terms in the model's equations. Here, X is the model state vector, whose tendency is this adiabatic tendency plus a diabatic tendency plus an error, because the model is not perfect. And so the whole idea of this approach is to specify this R as some small random number R between +1 and -1 multiplied by this diabatic tendency itself for every model variable at every grid point at every time step. And this R has between +1 and -1 typically has spatial and temporal correlation scales of say 500 kilometers and 6 hours. And this is used as an effective way to account for chaotic diabatic physics in the atmosphere as a stochastic term in models. And even this crude approach has proven successful at reducing this gap, mainly by increasing the ensemble spread of the forecast and less so by decreasing the forecast error. And I should, as described in all these papers in some detail, including some papers from ECMWF and NCEP. But I want to stress that this is actually a fairly drastic randomization of the diabetic tendencies. These diabetic tendencies are the hard-won knowledge, encapsulates the hard-won knowledge of physical processes in the atmosphere from decades of model development and field experiments and what have you. And the claim here is that if you take those diabetic tendencies and just multiply them by a random positive number between 0 and 2, then you don't only degrade the forecast, but you actually improve the forecast, which is actually, I find, quite disturbing. So this is what happens in our experiments. So when we implement the simple stochastic parameterizations of this form in the GFS model, which is the precursor to the UFS system, then we find that it not only increases the spread of these forecasts from say day 0 to day 15, but also reduces the forecast error, or error of the ensemble mean forecast. So these results were obtained for 80-member ensemble forecast for 80 distinct forecast cases in the January to March 2016 period. And these forecasts were made both with and without the stochastic parameterizations. And so without the stochastic, and this is shown for four kind of hard to predict variables in the atmosphere, but which are important for weather. And so upper tropospheric vorticity, mid tropospheric vertical velocity, column precipitable water, and 2-meter air temperature. So the effect of the stochastic parameterizations in all cases very robustly is to increase the spread, as found by almost everybody else. But in our experiments, we also see a clear reduction in the error of the ensemble mean forecast throughout the forecast range, including near this, say, past day 10, when the curves are beginning to sort of flatten, meaning that this is also improving the climate of the model. So the striking thing to me about these experiments was that we see these effects not only beneficial impacts, not only in the ensemble spread, that is by increasing the ensemble spread everywhere for these variables, but also decrease the RMS error and in a geographical sense, almost everywhere. And this, to me, this precip result is really quite striking, because this is being verified against an observational data set. In this case, I believe it's the NASA GPM data set, but we get practically the same picture when you verify these ensemble mean forecasts against the Persian data set. And these stochastic perturbations also make the probability distributions of the 12-hourly, that is the sub-daily precipitation, more realistically skewed and heavy-tailed. So this is what we get for the skewness and the kurtosis, which is a measure of the heaviness of the tails of the precip distributions of 12-hourly accumulations. And the contour, the shading interval here has been chosen carefully so that the shading here for the kurtosis is 1.5 times the square of the shading intervals here, shading levels here for the skewness. And this is done deliberately to see to what extent this kurtosis and skew satisfy this relationship k is equal to 1.5 s square, which is obeyed by gamma probability distributions, which are often claimed to be a good fit to precipitation, observational precipitation data. And this, these two upper panels resoundingly sort of confirm that relationship once you include the stochastic parameterizations and from the similarity of these pictures, even not just in terms of patterns, but also in terms of the magnitudes here, is showing that the kurtosis is very nearly equal to 1.5 times s square. And of course, this has great implications for representing the extremes of the probabilities of sub-daily precipitation. And the effect of the stochastic parameterizations here is to increase the skewness everywhere, as shown in this peach color, and also to increase the kurtosis very strongly in the tropics and less clearly in mid-latitude. But of course, kurtosis is the fourth moment. So if the mean is the first moment, variance is the second moment, and skewness is the third, this is the fourth moment of the ensemble probability distribution. And it is kind of slightly more sensitive to sampling errors. But just to show the robustness of this result, we have actually generated large 40-member ensembles of AMIP simulations with the FP3GFS model for a 20-year 1999 to 2018 period, and looked at all these statistics. But just to make a clean comparison with this picture here, shown using the GFS model for that January to March 2016 period, we're showing results for the precipitation skewness and so on in exactly the same format as the previous slide. And again, you see that there's an approximate relationship of 1.5 kurtosis is equal to 1.5 times q squared, although it's not quite as clear as in this earlier version of the model. Basically the difference between this model and the earlier model is this dynamical core, as everyone knows. But the impact of the stochastic parameterizations on the skewness is again very clear. It's to increase the skewness and also to increase the kurtosis, especially over North America. So here is actually one of the main results from this large ensemble of FE3GFS simulations that were generated both with and without the stochastic parameterizations. So the upper panels show the mean precipitation, 20-year mean precip in this ensemble mean, 40-member ensemble mean. And you see it's a reasonable field. And I believe, although I don't carry these pictures in my head, I believe this double ITCZ problem is slightly less severe in this FE3GFS model. And on the right-hand side, you see the standard deviation of the 6-hourly precipitation totals. The picture, the pattern of this looks very similar to the pattern of the mean precipitation, but the amplitudes here are larger. In fact, the ratio of this over this is a very good measure of the skewness of the precip distribution, if the distributions are roughly gamma distributions. And the fact that these numbers are almost everywhere greater than 1, again, confirms the fact that in these FE3GFS simulations, the precip distributions, sub-daily precip distributions are indeed strongly skewed, and that's a nice result here. But one of the main results here is the effect on the mean precipitation, climatological mean precipitation, and this is shown as a fraction. So the numbers here are basically showing that these are of the order of about, say, 5% for at most locations on the globe. Interestingly, the stochastic perturbations lead to a slight drying of the mean precipitation over North America, and that appears to be connected with this kind of stronger drying to the southwest of North America in this atmospheric river region. And consistent with that interpretation is also a decrease in the standard deviation of the subdaily precipitation, 12-hourly precipitation, 6-hourly precipitation totals in this case. And so is this actually an improvement in the statistics? We don't yet know. We have only recently finished these runs. And but definitely this is something worth exploring, since it obviously has large implications for extreme precip events over North America. So what's going on here? I mean, how do we make sense of all these results with these by putting in the stochastic parameterizations of the form P of x times r, where r actually has a zero mean? How are we able to increase not only the variance? I mean, that's not a surprise, since after all, you're shaking the model more. But if r is a zero mean, then how are you affecting the mean climate and changing the shapes of the distributions? And that seems kind of mysterious, but in fact, it's not mysterious. It's a very simple and robust explanation here if you just think about it the right way. And for example, if you just think of a px, expand that in a Taylor expansion around some mean value, and just retain the first two terms in that expansion, so as some g plus e times x times r, and then try to investigate what are the implications, what are the effects of this kind of forcing in the very simplest linear Markov models, as shown in these two upper and lower kind of pictures here. Then you understand these basic results obtained in the GCMs. And so what this is showing is the simple Markov model. And if you just focus on the effect of this additive part of the noise, which is not state dependent, and so this is simply G times R, then you're only kind of increasing the stochastic forcing, amplitude of the stochastic forcing, and that increases the variance of the ensemble spread, and also the climatological variance. But it doesn't change the ensemble mean forecast, and it doesn't change the mean climate. So on the other hand, if you also consider the effect of this a multiplicative noise term, E times X, and we call this multiplicative because the random numbers are being multiplied by X. And then two things happen. First of all, you increase the noise further, and you also make it asymmetric with respect to the sign of X, and you make it stronger for large values of X, and these will tend to make the distribution kind of skewed and heavy-tailed. But there is also this important effect here, which is a kind of a rectified effect on the mean. So even though R itself has a zero mean, the product E times X times R does not have a zero mean, even for over short intervals, like say 6 hours. And so this shows up rigorously in this equation as a minus half E squared term, even over short intervals, and a minus half EG term as a long-term mean kind of rectified effect. Think of this as effectively time mean Reynolds stress associated with chaotic sort of processes in the atmosphere. And so this is how, by putting in this this kind of noise, you can affect the not only the variance but also the means and the shapes of the distributions, as we found at the GFS experiments. And so to recap, randomizing the parameterized diabatic tendencies P of X in a model as 1 plus R times Px is a very crude but effective way to account for chaotic physics in the real atmosphere. And our sort of conception of this whole stochastic parameterization agenda is kind of illustrated here in this cartoon on the left. And so let's say your parameterized diabetic tendencies are, say, this thick blue, thick red line. And the real diabetic tendencies in the atmosphere are represented by this very thin blue line, which is not only a rapidly varying function of the state variable X, but also is very sensitive. The whole functional form itself is very sensitive to say, the parameters, real parameters of this diabetic processes. And so we have to represent that somehow in this model. And one way is to continue to refine your P of X until it gets that. But that, from the logic I just gave you, that seems like a hopeless task. Just from the rapidity of these variations and their sensitivity, it's basically chaotic. That's what we mean by chaotic physics. And so maybe the best thing one can do is simply to slap on some random perturbations of the form R times P of X around this red curve, and shown by the peach swath, whose amplitude may sort of depend upon the amplitude of X. And maybe that's the best one can do. And you have to be mindful, of course, of the specified space and time scales of these perturbations, and also the amplitude. For example, if your model has the diabetic tendencies, parameterized diabetic tendencies out of this black sort of curve, which is more chaotic than the red curve, then maybe you don't have to put in as many stochastic perturbations. In any case, you have to do something, and what we have been showing so far, just doing something like this, 500 kilometers in 6 hours, and folks at ECMWF and also at NCEP operationally use 5 sets of numbers. And it's the ad hoc nature of these numbers that have given this so-called, this whole stochastic parameterization agenda kind of a mixed reputation, or even a bad reputation in certain communities, sub-communities of our field, especially for the climate modelers, one of whose main objections is, okay, by putting in terms like this, you have increased the ensemble spread and make the forecast uncertainty more reliable, in the sense that the actual reality tends to fall less often outside your indicated spread. But this is very different from saying that you've actually improved the model. And what does it say about improving the model's kind of sensitivity to, say, global warming or El Nino or aerosol forcings or whatever? And so we partly agree with that criticism, and for that reason, we want to try to come up with better justified and better specified space and time scales and statistics of these random numbers are. And one way that we are thinking of doing this is to observationally constrain the statistics of this R using the statistics of the initial tendency errors, capital R, and the statistics of PX. And this is the approach we have followed so far, and this is still ongoing work, and you can see it's actually really a massive calculation. So thank you, Gil, for doing this in very difficult personal circumstances. But so the idea of this observationally constraining the statistics of this R is to approximate the initial tendency error R that you get in the forecast without stochastic parameterizations as this R times P, where P is the parameterized diabetic tendency, and then use the very simple relationship among the covariances of these three quantities to sort of estimate or back out the covariance statistics of the small r, given the covariance statistics of the tendency errors and the covariance statistics of the P that you know. And so all the hard work goes into finding the determining the covariance statistics of the tendency errors, and we in fact use the statistics of 2R forecast errors for this purpose. And this is a massive calculation where we have run 80-member ensembles for every hour in the 6-month June to September 2020 period, and verified these forecasts, determined this R with respect to analysis, hourly analysis performed using a customized hourly data assimilation system that uses this weather application model of the UFS at 50-kilometer resolution. So this is just a sampling of the results here for showing the estimated space and time scales of the random part of the 850 millibar humidity tendency and the 850 millibar zonal wind tendency. And the take-home message here is that these the colors are all purple, and if you look at the color bar below, that shows that these values are all generally larger. Both the space scales and the time scales are generally larger than the 500 kilometers and the 6 hours we specified in our experiments. And who knows, if we had used these longer scales, we might actually have gotten even bigger impacts of the stochastic perturbations in our experiments. So just to summarize here, many previous studies have already demonstrated improvements in the probabilistic forecast skill through increases in the forecast ensemble spread generated by randomizing the parameterized diabetic tendencies in this manner. However, we have stressed that such a randomization can also improve the mean skewness and kurtosis of the forecast distribution throughout the extended forecast range. And they also improve the models. They also change the model's mean climate and variability and increase the model sensitivity to external forcing through these noise-induced modifications of the deterministic evolution operator of the model. And we have argued that these additional effects arise in effect from such stochastic noise-induced drift. And I don't want to gloss over the fact that these stochastic impacts are generally found to be appreciable only when the specified space and time scales of the random perturbations are much larger than the model grid size and time step. And so such large scales are hard to justify if the stochasticity is meant to account only for chaotic feedbacks from the unresolved scales, as is usually done. In fact, our whole view is that such large scales are accounting for the chaotic physics on the resolved scales. And such larger scales are better justified and better specified if the statistics of the are observationally constrained by the statistics of the short range forecast errors. So I think I'm slightly over time, but I'll stop there. Thank you.
Okay, thank you very much, Prashant. And yeah, we do need to move on to our next presenter. And Rochelle, I'm going to go ahead and make you presenter now. There we go. And so, Prashant, there is at least one question currently being typed into the discussion document. question for
Uh,
you there.
I
So,
can't. Can you read it to me? I can't see it from where I
well,
am.
if you can go into the discussion document, that would be great. Can you see the chat
Yeah, I can see
box
the
off to
chat.
the side? There should be a link there to this discussion document.
Right, right, right. Okay.
So
Uh,
if you can go in there and answer any questions that people might have, that would be great. So we can go ahead and let Rochelle get started here.
yeah, the answer to the first question was, can I just say what the question and answer was?
Well, can you do that in the document? We need to give Rochelle enough time here.
Right.
Yeah, I
Well,
appreciate you.
we just start about 6 minutes late, so I know we are running over time here, but okay, I'll do that in the discussion document.
Okay, yeah, everybody can see into that document there, so
Oh, I see.
everybody should be able to get your answer there.
Okay, thank you.
So, yep. Okay, Rochelle, I'm going to go ahead and turn it over to you.
Okay, thank you, Mark. And yeah, so we're going to focus on a similar goal to Prashant's on work to improve the ensemble errors and the spread of the ensemble. And in this case, we're going to focus on the model after the fact. So we're working with the model output and trying to post-process the output to improve these systematic biases and ensemble spread errors. So I'm going to talk about the work that my co-authors, Michael Scheuerer and Tom Hamill, as well as my other collaborators mentioned here, have been working on to use neural networks to do this post-processing of probabilistic weeks 3 to 4 precipitation accumulation forecast. And this is a project funded by the WPO, and it's a joint technology transfer initiative in collaboration with the Climate Prediction Center. Okay, so the Climate Prediction Center currently generates subseasonal precipitation outlook maps, as well as map discussions that go along with it. And you're likely familiar with these, but just to go over, these maps indicate regions where the precipitation accumulation at weeks 3 to 4 are above or below normal, and they're probabilistic, so the darker shades indicate regions where the ensemble forecast is more confident, and that the precipitation will be in these particular categories. And so for this subseasonal time frame, these forecasts can be used for a variety of applications, but some of them are managing water resources, monitoring ongoing and building droughts, identifying locations and times of enhanced or suppressed wildfire risk or flood risk. And so our methods that I'll talk about in this presentation, the goal is to improve the guidance that can be provided in figures like this through or potentially artificial intelligence, given the outcome of these. So an overview of post-processing and the ultimate goal of why we're using post-processing applied to our weeks 3 to 4 forecast are to yield skillful forecasts that more accurately can quantify the level of true uncertainty of the forecast. So in this toy example of annual temperature here, we can see that the observation is in blue and the ensemble forecast is in gray. And in this situation, this forecast has a warm bias and it should be adjusted. So we can adjust the mean of the forecast to be calibrated to align more with the true observation. But in the case of ensemble forecast, we also want to adjust the spread so that in times when the forecast is uncertain, that the spread is wider and the true observation more often falls within this ensemble. So to perform this post-processing techniques and to develop our algorithms, we use 20 years of past forecast and observation pairs, where our forecasts come from the Global Ensemble Forecast System, or GEFS v12. And these forecasts are for 20 years with 11 ensemble members available once per week. And this is at half degree horizontal resolution, and our focus is over the contiguous US, or CONUS domain. And the variable that I'll be focusing on today is the total precipitation. And I've accumulated that over multiple weekly timeframes. And this presentation will focus on weeks 3 and 4. And to verify and train our models, we use the PRISM Zaley gridded total precipitation dataset as our ground truth. And we use this for the same accumulated time periods. So the neural network task that we're first exploring is developed by Michael Scheuerer et al. In 2020 Monthly Weather Review as a co-author in that paper. And the goal of this project is to expand the work that was initially done in that paper that demonstrated that neural networks could be used to post-process precipitation over California during the cool season. So this project is trying to use those similar methods to post-process precipitation over the full CONUS domain in all seasons and add additional development to that. So this task is for each grid point across the domain, predict the probability of precipitation forecasts falling within 20 different precipitation bands defined by the local climatology. And this, I will use an artificial neural network separately for each month and lead time. So I'll train a separate one for each of these. And the predictors that go into this one are just going to be initially first 3 predictors. It's going to be normalized precipitation forecast in the form of what's called an extreme forecast index. This just gives us a value that's not contingent on the local climatology. So, and it's also a value between -1 and 1, which is helpful for our neural network. And also we're providing it normalized geographic information such as latitude and longitude. And by doing this, we're able to pull all of our grid points together across the full domain and train one neural network that can work across the full US domain. So this is a schematic of what this ANN looks like. So on the far left, we have the gray arrow, which indicates our 3 input predictors. And then it goes into this first hidden layer where we have, which is the green. And these have separate neurons where essentially this is a weighted sum of all of the input predictors. And the outputs from those go into what's called a nonlinear transformation function. And this is really where the benefit of a neural network comes from, is where it can introduce and learn from nonlinear interactions between all the different predictor variables and learn that information on how it might affect precipitation forecast coming outside of the neural network. And so after that first initial layer, it goes into this preliminary output layer, which is in yellow. And you can see here there's 20 different neurons to represent the 20 different category bins of precipitation. And one unique aspect of this neural network is once we have those different outputs for each category, we add in a layer where we incorporate the climatological probabilities. And this helps ensure that if the network shows that there's not really any skill at predicting these probabilities, that it can at least collapse back to a climatological forecast, so that our forecast would hopefully not often be worse than a climatological forecast. And in the final layer, we apply a softmax activation function here in orange. And this just makes sure that our categories probabilities can actually be interpreted as probabilities of being in particular categories. And from there, we can interpolate between the different categories to get a full predictive distribution of accumulated precipitation, from which then we can sample different ensemble members from that, or we can pick out the probability of exceeding certain thresholds like above or below normal. So in addition to using climatological forecasts as a benchmark, we also wanted to look at how these methods compare to a more traditional statistical approach for post-processing. And for this, we use the censored shifted gamma distribution, or CSGD method. And this is a grid point by grid point method. And it is a state-of-the-art parametric method for precipitation accumulation, and particularly for shorter or medium range forecasts. And so we're extending it here to see its performance at these longer timeframes. And the big takeaway from this method is that we're using multiple regression equations to link the raw ensemble statistics, so the mean and the spread of the ensemble, to figure out the parameters of the predictive CSGD distribution. And this distribution is able to account for the unique characteristics of precipitation, such as having heavily skewed tails at the higher end, and also the mixture of precipitation being a discrete and continuous distribution. So moving on to some initial results, we can look at continuous ranked probability skill scores, where a positive skill is in red, and that indicates that the metric, or that the forecast, is an improvement over a climatological forecast. So we see here for the ANN approach that there's red over most of the US here, and this indicates that the neural network is more skillful than a climatological forecast at weeks 3. And we also see that for the traditional CSGD method as well. But as we get to week 4, we start to see some deviation between the two methods, and that both of them are less skillful. There's lighter shades of red here, and that's to be expected with longer lead times. But we can see that the ANN overall is able to retain more of the skill across the full CONUS domain, while the CSGD starts to break down in some areas and not have as much of a broad overall skill across the US. And we also look at the reliability of these forecasts, and this is still preliminary work, but this is showing the forecast events of being above the 33rd percentile of climatology for January at weeks 3. And a perfectly reliable forecast would lie along this dashed diagonal line, and the different colors represent the different forecasts. So the ANN approach is in red, the CSGD is in blue, the raw forecast output for the model is in black, and a simple unbiased forecast where the percentile of climatology is based on model climatology instead of observations is shown in green. So what we see right here is that the ANN needs some improvement on the reliability. It's not as reliable as, say, the CSGD approach at this time of year and at weeks 3, but it is more reliable than say the raw forecast, especially at these higher forecast probabilities. The raw model is overconfident. And when we look at an above normal event, we see that the raw model is really overconfident, especially at these higher forecast probabilities. And the ANN and CSGD are able to provide a little bit more reliability at these forecasts. And when we look at week 4 for these same events, we notice that the ANN is more reliable than the raw forecast, but it's overconfident, or it's showing that it's consistently overconfident to some degree. And we also see that the ANN is not comfortable making a forecast probability that deviates much from a climatological forecast probability at this time. And this just indicates that it's not showing that the forecast is super confident at issuing above normal forecast at this time. So when we look at now the summer months, so we look at July, and we can see that the ANN and CSGD compared to this previous plots has less skill overall compared to January, but the CSGD starts to deviate more in its performance compared to ANN. And we can see that in particular in the dry regions, say in Southern California, where this might be due to overfitting, since it's a grid point by grid point method at those dry locations where there's fewer above 0 or greater than 0 precipitation events to train the model with. And at weeks 4, this becomes even more apparent, while the ANN is able to retain overall skill scores across the US. And some good news for the ANN approach is that in the summer months at week 3, the ANN forecast is nearly perfectly reliable for each of these events. And also, when we look at weeks 4, the week 4 is nearly similar in the reliability from week 3. And again, the forecast probabilities that it's issuing are lower as we get to these more above normal events, as it's showing that it's not confident making these high forecast probabilities. So in summary of the ANN, we used a single ANN post-processing model for the entire domain, and based on this initial demonstration paper by my co-author, Michael. And the ANN method had comparable skill scores to the CSGD or traditional approach at weeks 3 in January, but it retained skill better than the CSGD at weeks 4. And the artificial neural network method had generally higher skill scores than the CSGD method in July for weeks 3 and 4. And this is likely due to the ANN pooling multiple grid points together and ultimately leading to less overfitting issues, especially at dry locations. And the reliability of the ANN still needs some improvement, especially in the winter months, is making overconfident forecast. However, the reliability of the ANN in July is nearly perfect. So what we're working on currently is also exploring whether we can get improved performance with the convolutional neural network. And the benefit of using a convolutional neural network, which is often used for image classifications, is that we can actually feed the neural network instead of a vector of values across the US, we can actually give it the full image, the 2D image of weather maps. So we can use normalized predictors. In this case, we're thinking of using large-scale predictors, such as normalized geopotential height at 500 millibars and total column water rather than precipitation, just to account for the large-scale weather patterns that might be influencing precipitation at a given location, especially considering that as we get further out in lead time, we're accounting, or we're less constrained by the initial conditions of the forecast, and we're starting to incorporate some more of these lower frequency patterns that are affecting our forecast. And so for that reason, we're also going to consider sea surface temperature anomalies and outgoing long wave radiation anomalies to help capture some of these tropical teleconnectors such as ENSO and the Madden-Julian oscillation. So the idea here is that we can use these different weather maps to be able to pick out certain nonlinear interactions between these fields and also tropical teleconnectors to see how this influences observed precipitation. So the CNN, it uses multiple small filters, which are learned by the network. And these filters essentially go over or slide over each of these images, and they're able to find and extract certain characteristics within these different weather maps. And then they're combined from all the different weather maps that are given and to figure out the nonlinear pattern information among them and how that can influence the observed precipitation. And then from there, we pass this through our artificial neural network to be able to get the probability of precipitation categories for the 20 different precipitation bends to ultimately get our full predictive distribution. So just bringing it back to the beginning, the goal of the artificial neural network and the CNN is to provide calibrated and reliable weeks 3 to 4 precipitation outlooks. This is still an ongoing project, but we're starting to see some encouraging results from the ANN, and we believe that the CNN would be able to give us even more skillful forecasts, especially as we get out to weeks 4, because we can incorporate these tropical teleconnectors more easily into the CNN. And so our methods here, the goal is to improve the precipitation forecast provided for the Climate Prediction Center. And given that this is a technology transfer initiative project, the ultimate goal is once we have our methods developed to put these algorithms up in near real time on a website at the Physical Sciences Laboratory to validate how these are working in near real time with future forecasts. And that is all that I had to share today. And thank you very much for inviting me for this presentation.
Great, thank you very much. Let's see, let me dig up the discussion document here. There are several questions being typed for you since we do have a few more minutes here. I'll go ahead and read them off to you, and then probably have you go in and maybe type in some responses as well. That would be great. But one question here is, does the GSGD method use stationary gamma distributions or the conditional distributions based on an equivalent stochastic dynamical process?
Yeah, so the CSGD method, it is starting from a gamma distribution, and then it is adjusting it in several different ways. And I would recommend going to that initial paper because it's a pretty involved distribution that was developed. But one of the characteristics is it's being censored at 0 for precipitation being a positive quantity. And also the shifted part is accounting for the fact that precipitation has a point mass at 0. So it's meaningful to have a particular probability associated with a perfectly 0 amount of precipitation. And Yeah, so I hope that answered your question there. I wasn't quite sure what you meant by the last part of that statement.
Okay. Another question here. Do you have a sense of where these improvements are statistically significant, i.e., did you compare to jackknifing or similar? And then also, how much independent data versus training did you use?
Yeah, these are great questions. So I haven't done the statistical significance testing yet, but that is something that we'll do once I have the more of the algorithm tuned. So we'll be able to determine how much more different it is compared to using the traditional methods and these different neural network methods. And yes, I divided my data out into independent data sets. So I have a training data set and a validation used for tuning, and then a separate test data set. And I'm using a leave some out approach. So my validation data set, or my testing data set, is 1 month for 1 year, and the training and the validation is made up of the remaining 19 years for a 3-month window around each of the months. So it's 3 different sets of data that I'm splitting it up into.
Okay. There's one more. Okay. Looks like she's done typing now. So it says, thank you for a great synopsis of your work. Launching from your final few slides, have you found that the CNN actually improves upon the ANN? In our work on S2S prediction and precipitation using large-scale precursors with ANNs, we haven't found CNNs to improve upon what our vanilla ANNs are able to do. So actually, they can be worse. So Elizabeth Barnes is asking this question. She's curious to see if this actually helps anyone else.
Yeah, thank you for your question, and that's good to know that from your experience you hadn't really seen too much improvement with that. I haven't gotten to the stage where I can look at I'm still kind of working on writing up the algorithm for the CNN, so I haven't been able to see the results from that. But the original demonstration paper over California showed that the CNN did provide improvement over California, mostly at weeks 4. So at weeks 3, it wasn't an improvement over ANN, but at the longer time frame, that's where we started to see some improvement, and they did do statistical testing on that.
All right, sounds like you two might want to talk a little bit offline here.
Yes, yeah, thank you very much for your questions.
Okay, I don't see any other questions for you popping in there right now. We have a couple of minutes left, and is Prashant still on? Yeah, I think he is here.
I meant for my talk to be longer, but it always goes faster.
That is usually the case, but so I'm going to ask Prashant if do you want to expand upon any of these questions that were given to you?
No. Well, just to say, in case any people in the audience haven't seen these questions, question number 1 was, it seems that we used additive noise in the model, and did you try multiplicative noise? And the short answer to that is no. One of the main points I was making was that the R times P of X perturbations we used in the models are already clearly multiplicative noises, because the amplitude of the noise P of X depends upon X. And the other question was, are these results improvements in the ensemble mean forecast expected to be kind of universally applicable? Have we looked at, say, all model variables at all levels? And the answer to that I wrote was that we haven't looked at everything, but and this is an important point, so thank you for asking this question. But our results are clearer than others, and not only in these global metrics of the curves I was showing, the error growth curves and the spread growth curves, but also the maps, and nobody else shows these maps, and the maps were very clear for the variables we looked at, that the the spread increased almost everywhere. Those spread maps, the impact on the spread maps was red everywhere, meaning an increase. And the impact on the ensemble mean forecast error was a decrease. They were blue everywhere. This is a really striking result. And the main reason we think this is happening in our system is that in the GFS experiments, we were able to go deep into the boundary layer and stochastically perturb the boundary layer quantity is very close to the surface. And for some reason that did not set off instabilities in the model. But many people find that they need to taper the amplitudes of these stochastic perturbations from the free atmosphere to kind of zero in the boundary layer, because it does set off numerical instabilities. And we had to do some of that in the FE3 GFS runs, and that may be partly, but not wholly, the reason why in the FE3 GFS runs we got slightly weaker impacts. But as I said, a lot of this is up in the air because so much depends upon the specified space and time scales of this noise. And we need to be less ad hoc about this, because it's that ad hoc nature that is giving this this whole enterprise sort of somewhat of an engineering fix kind of a bad smell. And we need to correct that by somehow linking these statistics of these random perturbations to the statistics of the short range forecast errors that you would get without stochastic parameterizations. So that way you can say that the random perturbations are effectively trying to get the statistics of this erroneous forcing through these stochastic perturbations with these space and time scales.
Okay, thank you. I'm glad we were able to kind of return to those questions. We are at the top of the hour here. If anybody does have any more questions and they want to go ahead, they can go ahead and put them in the discussion document at any point. And we'll check it again here in a little bit. If there's anything new, we'll go ahead and alert the speakers to that. Other than that, thank you very much for your attention, and thank you once again to our two speakers for their wonderful talks. And I hope to see everyone again next month.
Thank you.
Thank you.
Thank you.